Alright, so let's learn how to solve linear second order differential equations that are homogeneous and constant coefficients. So, this is the equation. So a second derivative of x plus b first derivative plus c x, a, b, and c are real numbers, constants. They're not functions of t. This equation is very important in physics and in engineering. We will actually have a full block called the harmonic oscillator dedicated to it. Can't wait until we get there. But for now, let's solve this one. Let's start from the beginning. All right, so again, there's gonna be infinitely many solutions, but we know because of theorem 1 and theorem 1 and theorem 2 that all that we need to do is find two independent solutions, and then the general solution will be the combination of the two. So our mission now is to learn how to find independent solutions for them, for this, and combine them. Okay, and then out of doing that, first we're gonna do the full nitty-gritty details of how to find those independent solutions. But after that, we will just learn an algorithm to solve it. Okay, let's go for it. All right, so it feels to me, if I look at that, I mean, it's usually I ask the class and you tell me every time. Okay, I need some sort of solution to this, right? That it needs to combine the function, its derivative, and the second derivative, and they have to cancel and be zero. It feels like the exponential could be a good candidate. Perhaps sines and cosines too, not why? Because the derivative of the exponential is another exponential. So yeah, it's very likely that you get combination of exponential that can cancel and give you zero, right? So let's try first. I mean, exponential is a natural guess for this. A function is derivative and second derivative have to be similar enough that they can cancel each other. Let's check if let's make an ansatz and let's check if an exponential solution works. If it doesn't, math will tell me. If it does, that's a nice thing, and we need to get used to that. You make guesses, and your guesses may be wrong. Math will tell you if they're wrong. If your guess is right, math will tell you, actually, that's a good guess. Well done. So let's see it. Let's see what happens. All right, so as we said, the exponential, so let's make the following ansatz. Maybe there is a solution. Maybe x of t equals e to the lambda t is a solution. Maybe and just maybe. That's the magic of the answers. All right. So let's plug it into the equation and see what math has to say about that. So if we plug this, let's call this 1, the equation 1, plug x of t into 1. What do we get? Well, easy, right? I mean, let's do it. X dot is equal to lambda e to the lambda t. X dot is equal to lambda squared e to the lambda t. Let's just plug it in. So we get a lambda squared e to the lambda t plus b lambda e to the lambda t plus c e to the lambda t equals 0. Nice! I can divide this by both sides by e to the lambda t, and what I'm left with is with this a lambda squared plus b lambda plus c equals 0. This is actually what we call the characteristic equation. Characteristic equation of the ODE. And in fact, we call this thing the characteristic polynomial. Polynomial. When you learn things in algebra, how to diagonalize matrices and so on, there will be something that you will call characteristic polynomial and characteristic equation as well. If they're called the same, and probably the professor who teaches that will use lambda as well, I don't know who they are, but I'm pretty sure, I'm gonna bet you that lambda is what this professor is gonna use for the eigenvalues of the matrices that you diagonalize. We'll see. Maybe I'm just, maybe I'm just going crazy. It could happen. But if not, let's talk by the end of the course about this. Anyway, for now, this is just names that we give it. let's go ahead with it. So, nice. The thing is that this equation, so look at what math is telling me. I asked math, is that a solution? And math told me, well, I don't know. If this is true, then yes. This is what math tells me. For that to be a solution, this equation has to be satisfied. But that's an easy equation on lambda, right? It's a quadratic equation on lambda. I know the solution. The solution is lambda is equal to minus b plus minus square root of b squared, minus 4 times AC divided by 2a. Wonderful! So I know that lambda, if I equate lambda to this thing is a solution. Not only that, there might be in principle 2 solutions. That would be great because 2 solutions is all that I need to solve that. Well, sometimes if this is 0, then I'm going to have only 1 solution. Well, maybe I have to be creative in that case to find the other one. But in general, I will have 2 solutions. If this is positive, there will be 2 real solutions. If this is negative, you would have 2 complex conjugate solutions. But at least, this is working. So let's see what happens. There are 3 possible cases. Let's say you have 3 possible cases. B squared minus 4AC being larger than 0. That means 2 real solutions. And then you can have b squared minus 4ac equals 0. So 1 double. So let's call it like 2 real roots for the characteristic polynomial, right? The characteristic polynomial has 2 roots that are real. Here we have 1 double root, okay? And in this, so you see, in this case, it would be the characteristic polynomial a lambda squared plus b lambda plus c would be equal in the first case to lambda minus something, let's call it lambda 1, times lambda minus lambda 2, 2 roots, 2 real roots. In this case, a double root, so in the second case, it would be something like lambda minus lambda 1 square, right, double roots. And the third thing that could happen is that b squared minus 4ac is less than 0, in which case we got 2 complex conjugate roots. So we get 1 root and it's complex conjugate. All right, so let's analyze every case independently and see what we get. Erasure. Okay, so we ask the question, okay, we have this equation and we say, well, is the exponential of lambda t a solution? We ask math, or the deities of math, and they said, yes, if lambda satisfies that. Wonderful then. Well, let's see, 3 cases. Case 1, when b squared minus 4ac is larger than 0, in which case we have 2 real roots, then we know there are 2 solutions. Then this is a solution for 2 different values of lambda. So we have an x1 of t equals e to the lambda 1 of t. We have another solution, x2 of t equals 2e to the lambda 2 of t, right? And of course, since lambda 1 is different from lambda 2, so lambda 1, let's just write the expression. Lambda 1 is minus b. Lambda 1 is minus b plus square root of b squared minus 4ac divided by 2a. And lambda 2 is equal to minus b minus root of b squared minus 4ac divided by 2a, right? These 2 are different, then we have 2 independent solutions, and that's nice because the equation is linear homogeneous, so I know by theorem 1, I know that I can combine the 2 solutions. I can write a solution x of t that is some constant with, let's call it c1, e to the lambda 1t plus some constant c2 e to the lambda 2t, and I know that's also a solution because of theorem 1, the superposition principle. But from theorem 2, I know that these 2 are independent. You see, this exponential with a number here and a different number here are not proportional. They're linearly independent. So therefore, this is the general solution. And nice, I got the general solution in terms of exponentials. Wonderful. That will be it for case 1. We will do examples later with particular numbers, but this is the way. So when you have a differential equation like that, and you get that b squared minus 4ac is greater than 0, the solution is going to be these two exponentials. Wonderful. Let's see case 2. Alright, let me do case 2, the one where the discriminant b squared minus 4ac is less than 0. So in which case we have two complex conjugate roots, and I write the two roots. Look, of course, the plus minus, if this is negative, this would be I times the positive root of the other one, of the changing sign, right, of 4ac minus b squared. So I write the two roots as alpha plus I theta and alpha minus I theta, where theta is this and alpha is this from that expression. Now you see that the two are complex conjugates. So you get one, you get the other one, changing the imaginary part of it, because the imaginary part of it comes from these roots divided by 2a, plus minus, so complex conjugates. Alright, so in this case, it's the same as before. They are different. Lambda 1 and lambda 2 are different. Therefore, we can write the solution, which I don't recommend you to write like this, but as a first step, we can have the solution. Well, we can write x1, it's equal to e to the alpha plus I theta times t. That's the value of lambda, right? And x2 of t would be e to the alpha minus I theta times t. Right. Sure, you can. And that means that I can write the general solution as, let me call this perhaps, I don't know, d1 e alpha t e to the I theta t plus d2 e alpha e to the minus I theta t, alpha t of course. Now it's really where d and d1 and d2 are actually in general complex constants, because we're getting into complex functions in here. Now we can actually realize that, well, this real equation has to have real solutions. So that way, which is valid for sure, is not the best way to handle them here. And for that, we go back to the very beginning. Remember your basic complex manipulation that we learned in one of the preliminaries videos? If you don't remember it, please stop this and watch it. Oh, it'd be nice if I could do this thing that they do on YouTube. There's a card in here that you can click and it will tell, I'm gonna do that. Well, I don't know where the card is going to appear, but okay, anyways. There's a card in here, probably, that will take you there, okay? And if not, you just go back manually to the list and check it, okay? Now, if you remember that, we actually saw and proved how the cosine of theta is equal to e to the I theta plus e to the minus I of theta divided by 2, and the sine of theta is e to the I theta minus e to the minus I, again, I write z for some reason, theta, divided by 2i. Right. Well, knowing that, I can define two different solutions, x1 tilde of t, which I'm going to call x1 of t plus x2 of t, and this is twice e to the alpha t. Well, it's the sum of the two, right? So the sum of the two would be e to the alpha t is a common factor, and it's multiplying e to the I theta, e to the minus I theta, which is actually the sum of the two is twice the cosine. So this is a factor 2 here, and this would be the cosine of theta. And look at that, how nice, this is real. And the same way I can do x2 tilde of t equals, I'm going to define it as x1 of t minus x2 of t, maybe divided by r. I mean, this one I can actually do divided by 2, much better. Divided by 2, so it cancels the 2. And this one I'm going to divide by 2i. And what I get if I do that is literally e to the alpha t sine of theta. So these are new solutions, x tilde 1, x tilde 2, that are linearly independent and are real. So I can combine them with x for the general solution as c1 cosine, well, I take the factor out, exponential of alpha t, and then c1 cosine of theta t plus C2 sine of theta t. All right, where C1 and C2 are real constants, arbitrary real constant. All right, instead of complex. So this is the general solution that I want. When you get the most convenient and more practical way not to have complications with complex analysis is find alpha 1, alpha 2, find alpha and theta, and then just directly you will be able to write the solution when you solve exercises. You don't have to repeat this. This is just so you know where it comes from. Look at that. So when this is true, the solutions oscillate. Harmonic oscillator, oscillations, oscillates with a frequency theta, and maybe they get damped depending on the sign of alpha, or amplified, who knows, depending on the sign of alpha. If B is positive and A is positive, then alpha will be negative. So this is it's like oscillations that die in a way. All right. Equivalently, we could actually give this other alternatively. We can combine the constants to a set of different constants. That can be done. These are the two constants are C1 and C2, but the sine and the cosine, you can rewrite them. So the sine or the cosine, if you want, can be rewritten as a sine plus pi over 2 and so on. Here's an exercise for you to practice. Prove that you can rewrite this as, in fact, we're going to do it. We're going to do this exercise when we see the phenomenon of resonance, which hopefully will be pretty cool, the phenomenon of resonance. There's many misconceptions about resonant frequency and natural frequencies, and we will actually deal with them here. We will do explicitly this transformation. If we don't do it, maybe I will give it to you as an assignment. I don't know, it's kind of easy. But you can rewrite this as this other one. A to the E alpha t sine of theta t plus delta, where now A and delta are constants. Or you could actually do the same thing, but with the cosine, E to the alpha t cosine of alpha t plus delta, which is basically combining the two using the sum of the multiple angle and so on. You can actually combine these two. Using trigonometry, you can combine these two into either a single sine or a single cosine. This is the one you're going to use by default in the course. These are the same with different values. A, you can find an A as a function of C1 and C2 and a delta as a function of C1 and C2. That gives you this expression. This can be converted into this. Now we will do it when we see the harmonic oscillator, and we will do it using tricks from complex manipulation. As an exercise, you can do it hardcore calculating. All right, you can actually use trigonometry. But you know what? Complex analysis saves you from trigonometric formulas. So we can do this transformation using complex analysis. How cool is that? We will do it when we see the harmonic oscillator. For now, I leave it as an exercise for you to do it the useful way, grinding. All right. One more case to go. Let's get to it. All right, so case 3. B squared minus 4ac equals 0. In that case, we're a bit screwed because we know it's a second order equation, requires two solutions, but because we have one double real root, we only get one solution, which is this one here. We need another solution. And I'm out of ideas because plugging in an exponential, you see sine functions and exponentials are two different sides of the same thing, you see? So sine function and exponentials, we already tried. That's not the case here. We need something else. It's not going to be just an exponential. But I'm out of ideas. What do you think? Let me show you the first person that came up with a way to solve this. It's Euler. And Euler thought, this is kind of magical in the nice kind of way. So let's see if you can enjoy it. Let's see with me. I mean, I don't know. If you like math a little bit, I think you will enjoy it. And if not, well, I may be wrong as well. Anyway, let me give you another solution. Maybe let me build this. Let me build an x auxiliary, no, I'm going to call it xa, but it's auxiliary. It's an auxiliary function, which is this one, e minus b 2a plus epsilon t. So this is not a solution, because the only solution that is an exponential is b over 2a times t with epsilon 0. But you know, it is a solution, in the limit epsilon going to 0, right? In the limit epsilon going to 0, this becomes a solution. It's not outside of the limit, but yes in the limit. Do we agree on that? So the limit of xa, right, is exactly x1 of t. So nice, yeah, it is a solution. It's the one we know in that limit. It's a different function that in the limit becomes a solution. Okay, but let me build an x2 of t that I say is a solution using the superposition principle, theorem 1, a sum of two different solutions. Let me build a solution that is the following. 1 over epsilon as coefficient, e, this solution, to the minus b over 2a plus epsilon t minus 1 over epsilon e to the minus b over 2a t. So, this thing that I wrote would be for any finite value of epsilon, it would be a solution, because it's a combination of two solutions, x ox and x1, only that actually this is not a solution. Only in the limit epsilon going to 0, this is going to be a solution. And then you may say, yeah, but in the limit epsilon going to 0, maybe this explodes, right? And this is not well defined. Maybe, but maybe not. Let's check the limit. If it explodes, math will tell me, you see? If it doesn't, if it's correct, if it's a good one, then the limit will exist. Let me define this as the limit when epsilon goes to 0 of this combination of the two. Now I know that in that limit, this thing is a solution. So this is the combination of two solutions. Now perhaps it's an ill-defined combination. It looks like I'm dividing by 0. Looks like, but maybe I'm not. This is the thing with limits. It certainly looks like I'm dividing by 0 and I cannot do that. But maybe I'm not. Again, imagine that I'm not dividing by 0. If we were not dividing by 0, this is one solution in the limit minus another solution in the limit, so it is a solution. Okay, well, let's see what happens. I hope that you are like, what? No, that can't be, and then you have a ton of questions for a live session. This is how limits work. Let's see what this limit is. So maybe it's just all ill-defined and wrong, right? I don't know. We'll see. Now would be the limit of, let's put everything in a fraction. This would be epsilon is a common factor, and I have e to the minus b over 2a plus epsilon, all multiplying t, minus e to the minus b to a, all multiplying t. So we have my solution, my almost solution. There's the difference between the two. Let's take that limit. So we can take as common factor e to the minus b over 2a. So this thing can even, there's no epsilons in it, so it can come out of the limit, e to the minus b over 2a. And now this, what remains is the limit of epsilon going to 0, e to the epsilon t minus 1 divided by epsilon. Now you can do L'Hopital here if you want. It's actually pretty easy to do L'Hopital. In the notes I actually do L'Hopital for you guys, but I promise to you that we will be using Taylor expansions. Let's do Taylor expansion, which is the actually easiest way. So if we do Taylor expansion, let me just copy that step just for reference. So this is e to the minus b over 2a. This is just copying. Limit epsilon going to 0 of e epsilon t minus 1 divided by epsilon. All right, the Taylor expansion of the exponential, so I copy minus b divided by 2a. Taylor expansion of limit epsilon going to 0. And then the Taylor expansion of that is 1 plus epsilon t. So let me just write 1 plus epsilon t, and I don't need more than that. Minus 1 divided by epsilon. The 1 and the 1 cancels, and the epsilon cancels. So this is e, so t, this is t. The result of this limit is t. So this is t times e to the minus b over 2a. Now look at that. This is x2 of t. And this thing is strictly a solution. In fact, if you plug it in here, you will see that it's correct. And it gives you a solution. So I was not dividing by 0 anything really, because the limit was an indetermination, not a division by 0. And it's one that has solution. So I found a solution x2 that, look, compare with this. It's different. I got two independent solutions. And because they're independent, and check that it's a solution. I leave it to you, please. Oh, I'm missing the T in here, my bad. Oh, I'm missing the T in here in all the steps. I'm the worst. My bad, it's multiplying t, huh? Remember that. Anyway, so this solution that I found, minus b divided by 2a times t, exponential of minus b t, maybe I'll put the t here, exponential of minus b divided by 2a times t, okay, multiplied by t is another solution to the equation, and then I found the general solution, x of t is equal to c1 e to the minus b divided by 2a t plus c2 t e to the minus b divided by 2e t, or if I simplify, that would be e to the minus b t divided by 2a multiplying c1 plus c2 t, and that is the general solution to the equation. Now let's recap and marvel on what we've done. In this case, we only had one solution out of our ansatz, so we need another. Maybe by inspection you can plug in that one and get it, sure you could. But we were a little bit tricky to find it, and we say, let me build something that is not a solution, but almost. In the limit of epsilon goes to 0 is a solution, and let me build a combination of that almost solution and the previous solution with a coefficient 1 over epsilon. This is only be a legal combination when, of course, this is not ill-defined, and second, in the limit epsilon going to 0. But it looks like it might be ill-defined, right? Because 1 over 0, what the heck are we doing? But then when we actually compute the limit, we get that this is a well-defined function, and this well-defined function, when epsilon goes to 0, is the other solution that we were looking for, and we combine them to find the final general solution. How cool is that? This is the original way this solution was found. How cool is that? I really like it, and I hope that some of you really like it, that some of you are like, nah, that can't be, and then talk to me about it, and we all discuss a little bit and enjoy this. Let's try to make the most of an online course and actually focus on discussing more. There's not gonna be midterm, there's not gonna be a final exam where you're there alone without being able to check things and so on. So let's actually take advantage of this to enjoy and discuss, and let's see if we can enjoy the course as much as we can. I mean, we can do the best with what we have, right? Anyway, let's do some examples, like one example of each, and that will be the end of this video. How about it? All right, let me quickly erase the board. All right, let's do this example. Find the general solution of 2x dot dot minus 5x dot plus 3x. So this is the same recipe for all these equations. First, let's find the characteristic equation, and let's find the roots of the characteristic polynomial. So let's write here, characteristic polynomial. So the characteristic polynomial is 2 lambda squared, remember square because it's second derivative, minus 5 lambda plus 3. That's the characteristic polynomial. Let's find the roots. So this thing will have two, well, maybe 2 or 1 roots, or I don't know what case it will be. Let's find it. Lambda is equal to 5 plus minus square root of 25 minus 4 times AC. A is 2, so 8 times 3, so that's 24, divided by 2a. 2a is 4. So that's an easy one. This thing is 5 plus minus square root of 1, which is plus minus 1 divided by 4. So we have 2 real roots. Lambda 1 equals 3 over 2. Lambda 2, it's equal to 1. All right, wonderful. So, case 1. This is case 1. 2 real roots. Okay, then I know what the solution is. The solution is x of t, it's equal to c1 exponential of the first root, 3 over 2, t, plus c2 exponential of 1t, so just t. And solved. Look how easy and how fast and how simple it is to solve this. Alright, so let's do another example. Alright, so in this example now, we have a different equation, second derivative of x plus 2x dot plus 5x equals 0. The characteristic polynomial is lambda squared, right, this coefficient, plus twice lambda, this coefficient, plus 5. that coefficient. Be careful, the mistake that some people do for some reason is just to still write lambda in the 5. For some reason I don't understand, but they do. So just tell you, please don't do it. Alright, so that means that lambda is equal to minus 1 plus minus root of 1 minus 5. I already simplified the divided by 2. Alright, so what does that mean? That means that we have two roots. We have lambda 1 equals minus 1 plus 2i. This is minus 4, right? So the root of minus 4 is plus minus 2i. And this is minus 1 minus 2i. As you see, two complex conjugate roots. So, case 2. Two complex conjugate roots. Okay, so we identify alpha in this case is minus 1. Remember that we said that alpha was equal, lambda was equal to alpha plus minus I theta. So alpha is minus 1 and theta is 2. Okay, so we go to the general expression that we found before. And when we got it, remember, I'm going to write the general expression that we found before. The general expression was that x of t, it's equal to e to the alpha t multiplied c1 cosine of theta t plus c2 sine of theta t. Alright, well, but then let's just substitute. So if we substitute, we get x of t equals, so alpha is minus 1, so it's e to the minus t. And this is c1 cosine of 2t. That's the frequency, the theta, frequency of oscillations, plus c2 sine of 2t. And that's the solution. Not too difficult, right? Of course, alternatively, you could write the solutions as this. You could write them like x of t. Remember the other general solution that we saw? Another way of writing it is x of t. It's equal, for example, to a to the minus t sine of 2t plus delta. Remember, with the constants a and delta. This is an alternative way of expressing it, as we saw in the previous section. But it's a pretty easy exercise. I prefer this one in general. All right, except for when we see resonance, we're going to use this one, but I will generally use this one. And for exercises, that is fine, for the exercise that you solve. They're equivalent. All right, let's do the final example. And erase. All right, so in this example, you may notice that the 5 has disappeared. So it's very similar to the previous one, but slightly different. Let's write the characteristic polynomial. It would be lambda squared plus 2 lambda plus 1. That's the characteristic polynomial. And the roots, well, lambda is equal to minus b, is minus 2, plus minus square root of b squared, which is 4 times 4ac, which is minus 4 divided by 2. So this is lambda 1 equals lambda 2 equals minus 1, 1 double real root. Or in other words, this is what we call case 3. Alright, so we know the general expression for case 3. It was, well, it's e to the lambda t multiplied, where lambda is minus b over a, but it doesn't matter, it is lambda, multiplying c1 plus c2t. Well, we substitute in here, and we get that this is e to the minus t, because lambda is minus 1, c1 plus c2t, and that is the solution. And with that, we finish solving linear second order homogeneous differential equations. In the next video, important one, we're going to learn how to solve any order homogeneous differential equations. Any order. Slightly more complicated than just second order. Alright? So, without more ado, right, this is the end of the video, and I'll see you in the next one.